The moment of inertia, otherwise known as the angular mass or rotational inertia, of a rigid body determines the torque needed for a desired angular acceleration about a rotational axis. It depends on the body's mass distribution and the axis chosen, with larger moments requiring more torque to change the body's rotation. It is an extensive property. The moment of inertia of a composite system is the sum of the moments of inertia of its component subsystems. One of its definitions is the second moment of mass with respect to distance from an axis r, integrating over the entire mass. For bodies constrained to rotate in a plane, it is sufficient to consider their moment of inertia about an axis perpendicular to the plane. For bodies free to rotate in 3 dimensions, their moments can be described by a symmetric 3x3 matrix. Each body has a set of mutually perpendicular principal axes for which this matrix is diagonal, and torques around the axes act independently of each other. Introduction. When a body is rotating, or free to rotate, around an axis, a torque must be applied to change its angular momentum. The amount of torque needed for any given rate of change in angular momentum is proportional to the moment of inertia of the body. Moment of inertia may be expressed in terms of kilograms square meters in SI units and pounds square feet in imperial or US units. Moment of inertia plays the role in rotational kinetics that mass plays in linear kinetics. Both characterize the resistance of a body to changes in its motion. The moment of inertia depends on how mass is distributed around an axis of rotation, and will vary depending on the chosen axis. For a point-like mass, the moment of inertia about some axis is given by d2 meters, where d is the distance to the axis, and m is the mass. For an extended body, the moment of inertia is just the sum of all the small pieces of mass multiplied by the square of their distances from the axis in question. For an extended body of irregular shape and uniform density, this summation sometimes produces a simple expression that depends on the dimensions, shape and total mass of the object. In 1673 Christian Huygens introduced this parameter in his study of the oscillation of a body hanging from a pivot, known as a compound pendulum. The term moment of inertia was introduced by Leonhard Euler in his book Theoria Motus Corporum Solidorum seu Rigidorum in 1765, and it is incorporated into Euler's second law. The natural frequency of oscillation of a compound pendulum is obtained from the ratio of the torque imposed by gravity on the mass of the pendulum to the resistance to acceleration defined by the moment of inertia. Comparison of this natural frequency to that of a simple pendulum consisting of a single point of mass provides a mathematical formulation for moment of inertia of an extended body. Moment of inertia also appears in momentum, kinetic energy, and in Newton's laws of motion for a rigid body as a physical parameter that combines its shape and mass. There is an interesting difference in the way moment of inertia appears in planar and spatial movement. Planar movement has a single scalar that defines the moment of inertia, while for spatial movement the same calculations yield a 3x3 matrix of moments of inertia, called the inertia matrix or inertia tensor. The moment of inertia of a rotating flywheel is used in a machine to resist variations in applied torque to smooth its rotational output. The moment of inertia of an airplane about its longitudinal, horizontal and vertical axes determines how steering forces on the control surfaces of its wings, elevators and tail affect the plane in roll, pitch and yaw. Definition. Moment of inertia I is defined as the ratio of the angular momentum L of a system to its angular velocity omega around a principal axis. That is, if the angular momentum of a system is constant, then as the moment of inertia gets smaller, the angular velocity must increase. This occurs when spinning figure skaters pull in their outstretched arms or divers move from a straight position to a tuck position during a dive. If the shape of the body does not change, then its moment of inertia appears in Newton's law of motion as the ratio of an applied torque tau on a body to the angular acceleration alpha around a principal axis. That is for a simple pendulum. This definition yields a formula for the moment of inertia I in terms of the mass m of the pendulum and its distance r from the pivot pointers. Thus, moment of inertia depends on both the mass m of a body and its geometry, or shape, as defined by the distance r to the axis of rotation. This simple formula generalizes to define moment of inertia for an arbitrarily shaped body as the sum of all the elemental point masses dm each, multiplied by the square of its perpendicular distance r to an axis s. In general, given an object of mass m, an effective radius k can be defined for an axis through its center of mass, with such a value that its moment of inertia is where k is known as the radius of gyration. Simple pendulum. Moment of inertia can be measured using a simple pendulum, because it is the resistance to the rotation caused by gravity. Mathematically, the moment of inertia of the pendulum is the ratio of the torque due to gravity about the pivot of a pendulum to its angular acceleration about that pivot point. For a simple pendulum, this is found to be the product of the mass of the particle m with the square of its distance r to the pivot. That is, this can be shown as follows. The force of gravity on the mass of a simple pendulum generates a torque around the axis perpendicular to the plane of the pendulum movement. Here r is the distance vector perpendicular to and from the force to the torque axis. Here F is the tangential component of the net force on the mass. Associated with this torque is an angular acceleration of the string and mass around this axis. Since the mass is constrained to a circle, the tangential acceleration of the masses. Since the torque equation becomes, where E is a unit vector perpendicular to the plane of the pendulum, the quantity I equals Mr 2 is the moment of inertia of the single mass around the pivot point. The quantity I equals Mr 2 also appears in the angular momentum of a simple pendulum, which is calculated from the velocity v equals omega times r of the pendulum mass around the pivot, where omega is the angular velocity of the mass about the pivot point. This angular momentum is given by using math similar to that used to derive the previous equation. Similarly, the kinetic energy of the pendulum mass is defined by the velocity of the pendulum around the pivot to yield. This shows that the quantity I equals Mr 2 is how mass combines with the shape of a body to define rotational inertia. The moment of inertia of an arbitrarily shaped body is the sum of the values Mr 2 for all of the elements of mass in the body. Compound pendulum. A compound pendulum is a body formed from an assembly of particles of continuous shape that rotates rigidly around a pivot. Its moment of inertia is the sum of the moments of inertia of each of the particles that it is composed of. The natural frequency, to obtain where is the period of oscillation, the moment of inertia of the body about its center of mass, is then calculated using the parallel axis theorem to be where is the mass of the body and is the distance from the pivot point to the center of mass. Moment of inertia of a body is often defined in terms of its radius of gyration, which is the radius of a ring of equal mass around the center of mass of a body that has the same moment of inertia. The radius of gyration is calculated from the body's moment of inertia and mass as the length. Center of oscillation. A simple pendulum that has the same natural frequency as a compound pendulum defines the length from the pivot to a point called the center of oscillation of the compound pendulum. This point also corresponds to the center of percussion. The length is determined from the formula, or the seconds pendulum, which provides the tick and tock of a grandfather clock. takes 1 second to swing from side to side. This is a period of 2 seconds, or a natural frequency of pi radians second for the pendulum. In this case, the distance to the center of oscillation can be computed to be. Notice that the distance to the center of oscillation of the seconds pendulum must be adjusted to accommodate different values for the local acceleration of gravity. Katter's pendulum is a compound pendulum that uses this property to measure the local acceleration of gravity, and is called a gravimeter, measuring moment of inertia. The moment of inertia of complex systems such as a vehicle or airplane around its vertical axis can be measured by suspending the system from 3 points to form a trifilar pendulum. A trifilar pendulum is a platform supported by 3 wires designed to oscillate in torsion around its vertical centroidal axis. The period of oscillation of the trifilar pendulum yields the moment of inertia of the system. Calculating moment of inertia about an axis. The moment of inertia about an axis of a body is calculated by summing Mr. 2 for every particle in the body, where r is the perpendicular distance to the specified axis. To see how moment of inertia arises in the study of the movement of an extended body, it is convenient to consider a rigid assembly of point masses. Consider the kinetic energy of an assembly of n masses μ that lie at the distances r from the pivot point P, which is the nearest point on the axis of rotation. It is the sum of the kinetic energy of the individual masses. This shows that the moment of inertia of the body is the sum of each of the Mr. 2 terms. That is, thus, moment of inertia is a physical property that combines the mass and distribution of the particles around the rotation axis. Notice that rotation about different axes of the same body yield different moments of inertia. The moment of inertia of a continuous body rotating about a specified axis is calculated in the same way, except with infinitely many point particles. Thus the limits of summation are removed, and the sum is written as follows. Another expression replaces the summation with an integral. Here, the function ρ gives the mass density at each point, and the integration is evaluated over the volume 5 of the body Q. The moment of inertia of a flat surface is similar, with the mass density being replaced by its areal mass density, with the integral evaluated over its area. Note on second moment of area. The moment of inertia of a body moving in a plane and the second moment of area of a beam's cross-section are often confused. The moment of inertia of body with the shape of the cross-section is the second moment of this area about the z-axis perpendicular to the cross-section, weighted by its density. This is also called the polar moment of the area, and is the sum of the second moments about the x and y axes. The stresses in a beam are calculated using the second moment of the cross-sectional area around either the x-axis or y-axis depending on the load. Example calculation of moment of inertia. The moment of inertia of a compound pendulum constructed from a thin disc mounted at the end of a thin rod that oscillates around a pivot at the other end of the rod begins with the calculation of the moment of inertia of the thin rod and thin disc about their respective centers of mass. The moment of inertia of a thin rod with constant cross-section S and density ρ and with length about a perpendicular axis through its center of mass is determined by integration. Align the x-axis with the rod and locate the origin, its center of mass, at the center of the rod. Then, where m equals ρs is the mass of the rod, the moment of inertia of a thin disk of constant thickness S, radius r, and density ρ about an axis through its center and perpendicular to its face is determined by integration. Align the z-axis with the axis of the disk and define a volume element as dv equals c near dr d theta. Then, where m equals pi r2 ρs is its mass, the moment of inertia of the compound pendulum is now obtained by adding the moment of inertia of the rod and the disk around the pivot point P as where L is the length of the pendulum. Notice that the parallel axis theorem is used to shift the moment of inertia from the center of mass to the pivot point of the pendulum. A list of moments of inertia formulas for standard body shapes provides a way to obtain the moment of inertia of a complex body as an assembly of simpler shaped bodies. The parallel axis theorem is used to shift the reference point of the individual bodies to the reference point of the assembly. As one more example, consider the moment of inertia of a solid sphere of constant density about an axis through its center of mass. This is determined by summing the moments of inertia of the thin disks that form the sphere. If the surface of the ball is defined by the equation, then the radius r of the disk at the cross-section z along the z-axis is therefore the moment of inertia of the ball is the sum of the moments of inertia of the disks along the z-axis, where m equals 4/3 pi r3 rho is the mass of the ball. Moment of inertia in planar movement of a rigid body. If a mechanical system is constrained to move parallel to a fixed plane, then the rotation of a body in the system occurs around an axis k perpendicular to this plane. In this case, the moment of inertia of the mass in this system is a scalar known as the polar moment of inertia. The definition of the polar moment of inertia can be obtained by considering momentum, kinetic energy and Newton's laws for the planar movement of a rigid system of particles. If a system of n particles, pi I equals 1, n, are assembled into a rigid body, then the momentum of the system can be written in terms of positions relative to a reference point r, and absolute velocities v, where omega is the angular velocity of the system and v is the velocity of r. For planar movement, the angular velocity vector is directed along the unit vector k, which is perpendicular to the plane of movement. Introduce the unit vectors a from the reference point r to a point r, and the unit vector t equals k times a, so this defines the relative position vector and the velocity vector for the rigid system of the particles moving in a plane. Note on the cross product. When a body moves parallel to a ground plane, the trajectories of all the points in the body lie in planes parallel to this ground plane. This means that any rotation that the body undergoes must be around an axis perpendicular to this plane. Planar movement is often presented as projected onto this ground plane so that the axis of rotation appears as a point. In this case, the angular velocity and angular acceleration of the body are scalars, and the fact that they are vectors along the rotation axis is ignored. This is usually preferred for introductions to the topic. But in the case of moment of inertia, the combination of mass and geometry benefits from the geometric properties of the cross product. For this reason, in this section on planar movement, the angular velocity and accelerations of the body are vectors perpendicular to the ground plane, and the cross product operations are the same as used for the study of spatial rigid body movement. Angular momentum in planar movement. The angular momentum vector for the planar movement of a rigid system of particles is given by use the center of mass c as the reference point, so and define the moment of inertia relative to the center of mass ic as then the equation for angular momentum simplifies to the moment of inertia ic about an axis perpendicular to the movement of the rigid system and through the center of mass is known as the polar moment of inertia. For a given amount of angular momentum, a decrease in the moment of inertia results in an increase in the angular velocity. Figure skaters can change their moment of inertia by pulling in their arms. Thus, the angular velocity achieved by a skater with outstretched arms results in a greater angular velocity when the arms are pulled in. Because of the reduced moment of inertia, kinetic energy in planar movement. The kinetic energy of a rigid system of particles moving in the plane is given by this equation expands to yield three terms. Let the reference point be the center of mass c of the system, so the second term becomes 0, and introduce the moment of inertia ic, so the kinetic energy is given by the moment of inertia ic as the polar moment of inertia of the body. Newton's laws for planar movement. Newton's laws for a rigid system of n particles, pi I equals 1, n, can be written in terms of a resultant force and torque at a reference point r, to yield, where r denotes the trajectory of each particle. The kinematics of a rigid body yields the formula for the acceleration of the particle pi in terms of the position r and acceleration a of the reference particle, as well as the angular velocity vector omega and angular acceleration vector alpha of the rigid system of particles is. For systems that are constrained to planar movement, the angular velocity and angular acceleration vectors are directed along k perpendicular to the plane of movement, which simplifies this acceleration equation. In this case, the acceleration vectors can be simplified by introducing the unit vectors a from the reference point r to a point r and the unit vectors t equals k times a. So this yields the resultant torque on the system as where a times a equals 0, and a times t equals k is the unit vector perpendicular to the plane for all of the particles pi. Use the center of mass c as the reference point and define the moment of inertia relative to the center of mass ic. Then the equation for the resultant torque simplifies to the parameter ic as the polar moment of inertia of the moving body.